Greetings, future subjects. It is I, the evil genius. But I don't expect you to take my word for it. I will prove both of these things. First, I will prove the evil. Behold, I'm bald. Now, I will prove the genius. For now, I will show you with the enormous power of my mind, I will levitate this cube between my fingertips. Observe. If I were a politician, a CEO, or a financier, I'd try to explain that I had special powers, and that's how I did it. But unfortunately, I'm a scientist, so I'm going to show you the trick. Rule 17, it's always a trick. Up here, we've got a really powerful neodymium magnet. This is also a neodymium magnet. Now, if it's too close, it jumps up. There it goes. Bring it down a little more, gravity takes over, that's the stronger force, and it falls. Now, you would think you could get it just right, so it would hover right between, but that never happens. You can try all day. That's probably as close as I'm ever going to get. Right? That's too high, that's too low. You get it in between, it's going to be the one or the other. However, right, the water in my fingers acts as a diamagnet if it's in a strong enough magnetic field. And what that means is it expels the magnetic field of this, which means there's a bit of a repulsive effect. So between my fingers, both my fingers repelling, as long as most of the force of gravity is taken away by the attraction upwards, the repulsion from my fingers can get it to just about levitate between my fingers. And I'll just show you a couple other examples. So magnetic levitation. You should be able to get it with just a pair of magnets. So if I take two of them over, they repel. And if you get it just right, you feel like you should be able to get one floating on top of another. But it never, ever happens. In fact, there's even a theorem called Earnshaw's theorem that says this never happens. Presumably Professor Earnshaw tried this for about 2 weeks continuously, and everybody else took pity on him and just said, right, Professor, if you just stop, we'll name the theorem after you. Right? Very, very simple thing. You can't balance one magnet on top of another magnet. That's it. You can cheat, though. Look, magnets levitating. Yay. Unfortunately, not too exciting, because it's not floating. Yes, it's levitating, but it's still held in place by this dowel. So it doesn't really work. I'm not really convinced. We can do better than that. This is a great toy. It's called the Levitron. And what it has is a magnet in here and a magnet in here. Now, this magnet and this magnet repel, and it's just the same as Earnshaw's theorem, except if this is spinning, then as soon as it starts to fall one way, it spins around, starts to fall the other way, and if you get it just right, you get levitation. Trouble is, it's really, really difficult to get just right. Here's where you montage a whole bunch. That was almost perfect. I can do better than that, but I got places to go and things to do. So let's just stop there. We can do better. This here is a stack of neodymium magnets, and this is a piece of pyrolytic graphite right in here. Now, the great thing is about this stuff is it's got diamagnetic properties, and that means it expels the magnetic field. So if I put this on here, it'll float. There it is floating. So diamagnetism. Now, how does it work? Well, let me tell you a secret. Anytime a physics teacher has no clue, what they do is they wave their hands around and go quantum mechanics. Right? So how does diamagnetism work? Well, electrons, spin orbitals, Pauli exclusion principle, quantum mechanics. I don't really know. But it's a neat effect. Will it help me conquer the world? No, it's a very weak effect. We need something stronger. Magnetic levitation with some bite. Can I have a countdown? 3, 2, 1. Now, how does this work? This is aluminium. It's non-magnetic. Watch. Isn't attracted to that electromagnet. Just to prove it is an electromagnet, watch again. On, off. So, aluminium, non-magnetic. So what's the secret? Well, I'll tell you. First of all, a couple more tests. Another piece of aluminium, a little thinner, same effect. One slight cut in it, nothing. So what's the difference, right? Air gap, really high electrical resistance, right? Through here, it's non-magnetic, but it is a really good conductor. So if I put here AC current, you get a constantly changing magnetic field through here. And if you get a constantly changing magnetic field through the center of a conductor, you get electromagnetic induction. You get a big current generated in this. That current creates its own magnetic field. And because of a bit of a phase difference between the magnetic field from here and the magnetic field from here, it repels more than half the time, and so it flies up into the air. One more time. 3, 2, 1. I love that. Now, just to prove there's a really big current going through here, what I'm going to do is I'm going to hold it down for a bit. When you put a current through a conductor and you put it in a big enough current for long enough, what happens? Well, I'll show you. It gets hot. So, some more magnetic levitation, but it lacks a certain elegance. We can still do better. For my next trick, quantum locking. So, quantum locking. For this, I need several things. 1, some liquid nitrogen. This, for you scientists out there, is 77 Kelvin. For those of you in the civilized world, it's minus 196 degrees centigrade. Americans, it's minus 321 Fahrenheit. And yet, because I am the evil genius, I can still do this. Now, I have the liquid nitrogen. All I need now is a liquid nitrogen superconductor and the mighty glove of power. What, you don't think that looks threatening and powerful? I think it looks glovely. They don't get any better. You just get used to them. Now, with the mighty glove of power and my superconductor. is in here somewhere. This is now very cold, and with this magnet, I'll show you quantum locking. Behold. Now, this is slightly different from diamagnetism. This is called quantum locking or flux pinning. What happens is some of the magnetic field lines in here end up passing through the superconductor at various places where the crystals don't fit perfectly, and they're trapped there. Because if they move to the side, it's a superconductor, so it generates an electric current. A moving magnetic field generates an electric current, electromagnetic induction. And it generates it in such a way so that it opposes the change causing it. That's Lenz's law. So it pushes it back to where it was. So the field lines are held in place, therefore the magnet is held in place. Now let's take it up a difficulty level. Right, now my superconductor should be cold enough. Let's see. Oop. Behold, drat, it levitates. Unfortunately, there we go. One of the great things about quantum locking is the magnetic field lines are held in place, therefore the superconductor is held in place. And it's not just repulsion. Watch. See? Either way up. So it stays there at the bottom, stays there at the top. So it's trapped in place. It's not just until it warms up. It's not just magnet against magnet. One of the best things about it, though, is if there's another magnetic field line ready to take the place of the first one, you can get it moving along a track of magnets with no friction against the ground. This could be the basis of a magnetic railway. Okay, up. All right, let's cool it down again. There we go, held in place along its own little racetrack. And if we can do this, how long will it be before we can conquer the world? All right, minions. World conquest, phase 1. Have a look at the map. The UK is ripe for plunder. We begin here, and then the world. Hey guys, you want to see the world's worst magic trick? Look at this. Whoop. Hehe.